A warm welcome to all the viewers. In today's session of Tourism and Hospitality Research, I am going to discuss with you few important and quite easy methods of analyzing the normality of your data in SPSS. Not just that, I'll be also telling you two ways to transform your data in case it is a non-normal data. How can you transform that data using log and square root transformation in SPSS so that your data becomes more normal in nature and you can go ahead with the analysis. So let us start. How do we test normality in SPSS? Herein I have mentioned three different methods which you can use to assess the normality of your data. Method 1 says that you have to check the absolute skewness and kurtosis values of the indicators. If skewness is within -2 to +2 and kurtosis is -3 to +3, then we can assume a normal distribution. This is especially in case of univariate normality. So when you are assessing univariate normality, that is normality of each and every item or observable variable or the indicator, then we can go ahead with these thresholds. Second method says that check the z-score. How do we obtain z-score? We obtain z-score by dividing the absolute skewness or absolute kurtosis values by the standard error. This value should be between -1.96 to plus 1.96 in order to signify normal distribution. Method 3 says if absolute skewness or absolute kurtosis values is less than double the value of standard error, then we can assume normality of data. So there are different thresholds and different recommendations on how to find out how to assess the normality of data. You might like to go into the literature and check out how which different methods can be applied and which one can you use for your research. Now, let us come to the solution of the problem. So, one of the solutions recommended by the researchers is that you can do log transformation or you can do square root transformation. But both of these transformations have different purposes. Log transformation is especially used when you want to normalize positively skewed data. Square root transformation is more effective in normalizing negatively skewed data. In case of testing the normality, the hypothesis is distribution is non-normal. That is the alternate hypothesis for normality. And the null hypothesis for normality is distribution is normal. Now, in order to reject the null hypothesis, the p-value has to be significant. That means it has to be less than 0.05. So if the p-value is less than 0.05, I reject the null hypothesis and I say that distribution is not normal, right? But that is the reason when we do KS, Kolmogorov-Smirnov test, or we do Shapiro-Wilk test, we want the p-value to be non-significant, that is greater than 0.05 in order to signify the normality of data. Both of these measures have their limitations. Kolmogorov-Smirnov is used when your data size is large, especially more than 50. Shapiro-Wilk can be used if your data size is small, that is less than 50. But they are still very sensitive to the sample size. So researchers often recommend that in case of doing a KS test or a Shapiro-Wilk test, you can better assess the normality of data through the three different methods which I have assessed, which I have told you herein before this slide. Now let us find out practically how to do log transformation. And in case the data is negatively skewed, similarly you can do square root transformation. The steps are: go to analyze descriptive explore dependent variable, that is enter the variable whose normality is to be tested. Check on plots and histogram and normality plots with test. A special condition over here is data should not have negative or zero values. Whereas in case of square root transformation, it can also handle zero values and stabilizes the variance. Once you have assessed through this method that your data is positively skewed, okay, then what you have to do, you have to go to compute variable, target variable, and do the log transformation of that variable by choosing an arithmetic operation that is LG10. If needed to be done for negatively skewed, then create the reflection, which is LG10 bracket maximum value in that variable plus 1 minus variable. So it means maximum value, what is there in your data set. So you'll have to check the maximum value in your data series, enter that value and do plus 1 minus that variable's value. So that is how you create a reflection in case you want to do it for negatively skewed. But I would recommend here, in case it is negatively skewed, then you should use the square root transformation. That is more effective. And there's no harm in using log transformation for positively skewed and square root transformation for negatively skewed data in the same analysis. There's no harm because this can handle well the negatively skewed data and this can handle well the positively skewed data. So let us go to SPSS and find it out how this analysis is done. So here we are in our SPSS data sheet we are using for demonstrating all the sample. All the examples have been demonstrated through this data sheet, which consists of 204 respondents, 204 respondents you see here. And now we want to assess, say, I've taken out the mean of behavioral intention. So this is the mean for behavioral intention, which was measured through 4 indicators. Now, if I want to find out this dependent variable in my data, it could be any variable for which I want to find out the normality. So what will I do to find out the normality of this BI? So I've transformed them into scale by using the arithmetic mean, which I have demonstrated in my previous videos also. You might like to go back and check how to deal with Likert items and transform them into mean for further analysis. So the values have been transformed into mean. Now I'll go to analyze, descriptive statistics, and explore. And in the dependent, I'll enter the BI value, which is the mean score, interval scale. And in the plots, I should make sure that histogram and normality plots with test is ticked on. Now I click on continue and press OK. So I get the results. There are no missing values. See, 0% missing values, 204 respondents, valid percentage is 100%. And now I'll see the skewness. So you see here, skewness is 0.804. Ideally, it should be as close as to 0 as possible to indicate normality of data. Kurtosis is 0.463. So, in this case, how do we assess the normality? These are the absolute values of skewness and kurtosis in case you want to go with method 1, which says skewness value has to be between +2 and -2 and kurtosis has to be between +3 and -3. You can simply give that reference as a support for going ahead with the analysis. As you can say, my skewness and kurtosis is within the threshold limits prescribed by that reference source. If you go by the second method, which I told you in the slide, that is, you divide the skewness value, absolute skewness value, by the standard error value to get the z-score. So let us do it and find it out. In case it lies between -1.96 to +1.96, then we can say our data assumed to be normal. Now, I'll go to calculator. I'll do it in front of you so that we can assess the normality. So I'll put 0.804. This is 0.804 absolute value of skewness divided by the standard error, that is 0.170 to get the z-score. So you see the z-score is 4.729, which is much higher than +1.96. That means my data is not normal. And if I want to go with this method, I want to make sure before going further that my data follows the normality rules. So how to do that? Let us check the kurtosis value also. 0.463 divided by 0.339. 0.339. So this gives me 1.36, which is well within the limits of minus 1.96 to plus 1.96 z-score. And then I can say kurtosis is within the normal limits. There's no leptokurtotic or platykurtotic issue in my data. So, but there is a skewness issue. That's why we have the log transformation for positively skewed data. Now you see, it's a positive number, 0.804. It's not negative 0.804. We can assess the same through this graph as well. You see a tail tapering towards the right side. Tail tapering towards the right side in this histogram. That means it is positively skewed, right? Let me show you how to assess the third method, the normality through the third method. So for that, again, I check on my calculator. So this value 0.804 has to be lesser than the double value of 0.170. So what is the double value of 0.170? 0.170 multiplied by 2 gives me 0.34. So the skewness value in my case is 0.804, which is higher than 0.34. That means again, I cannot say using method number 3 that my data is normal. It's positively skewed. Now let us check how to resolve this thing. To resolve this issue of positively skewed data, which you see here in histogram as well, it's positively skewed. I'll go to the data sheet and create the log transformed variable of this BI. To do that, I'll go to transform, compute variable. I enter here log BI, and let me show you once more how I did it. Arithmetic LG10, I take it over here, and in this question mark, I have to put the BI value, mean BI, like this. You read here, log 10 expression returns the base 10 logarithm of number expression, which must be numeric and greater than 0. That's why there shouldn't be any zero value or negative value in my data set to do the log transformation. Now let us see whether this log transformation helps me in getting my skewness value close to the normal value, the prescribed normal value. I press on OK, and now I get a new variable that is log BI in my data sheet. Now I have to analyze the skewness in this log BI. So I'll go to analyze, explore. This was my previous mean BI. Now in place of this, I'll put log BI in the dependent list. In plots, I check histogram, normality plots with tests, continue, and display both histogram as well as normality plots with tests. Click on OK. Now you again see here valid percentage is 100%, total respondent is 204, and we analyze which variable? We analyze LG10 log of BI. Now the skewness is reduced, you see here, by using the log transformation. My skewness goes down to positive 0.025. Earlier it was 0.804. You see here 0.804. So it has drastically reduced to 0.025. That means my data is becoming normal using log 10. So what has happened? Now you see the histogram. It appears more like a bell-shaped curve. It appears more like a bell-shaped curve. So let me check it out. So I'll again go to the calculator. 0.025 divided by 0.170 gives me the z-score of 0.1470. So this is well within the limits of minus 1.96 to plus 1.96, right? So as per my method number 2, I've achieved the normality of my data. Let me check through the third method as well, which says that the absolute skewness value, this value 0.025, has to be lesser than the double value of 0.170. So what is the double of 0.170? 0.170 multiplied by 2 is 0.34. Now you see here, skewness value is 0.025, which is lesser than the double value of the standard error. It is 0.34. So again, through method 3, I have achieved the normality of my data. I can go ahead with saying that my data has achieved normality. For further analysis through parametric tests using log 10, I have assessed the skewness value, but you have to take care that when you go ahead with the analysis now onwards, you'll be using the log BI value, because this is the numbers which you assessed for normality. Similarly, if your data exhibits negatively skewed data, I showed you an example of a positively skewed data. In negatively skewed data, you can go ahead with square root transformation, which is again quite easy to do. Same method, you can do the square root transformation for negatively skewed data. In that case, in case of LG10, you have to use the expression SQRT, and in brackets you put the variable to get the square root transformed value, and then you go to the assessment of normality. Again, in case it's a negatively skewed data, it will come closer to 0. So I hope the video was quite interesting and informative for all of you. Thanks for watching and keep watching for more.